In section 1.3, relation between data structures and algorithms, we are told that data structures not only define how data is organized and stored, but also the operations performed on the data structure. We have an example of appending an item to a linked list, and we're shown that this requires a different algorithm than appending an item to an array. We can see that it is shorter, the algorithm, to append to an array, and it is slightly longer for a linked list. It seems that the more code we have, the shorter the runtime is. And the shorter code we have, the longer the runtime is. So knowing that, we're going to look over some examples. We're going to consider the array and linked list in the picture we just went over, and we're asked, can the following algorithms be implemented with the same code for both an array and a linked list? Can we append an item? And the answer for this is no. It's because the algorithms for appending an item require different algorithms for each implementation. Next, we're asked, return the first item. Well, the answer again is no. For arrays, we would be returning index 0, and for linked lists, we would just be returning the head. Lastly, we are asked to return the current size. This is the same for both of them because we would just increment the size and then return the size for both of them. We're given some pseudocode. Some algorithms utilize data structures to store and organize data during algorithm execution. And then we are given an example of an algorithm that determines a list of the top 5 salespersons. We may use an array to store a salesperson sorted by their total sales. So we have a method here. We're passing in all of our salespersons into here, creating an array of 5 elements. Our array elements have sub-items for name and total sales. Our array will be sorted from highest total sales to lowest total sales. And then we create an array with our 5 elements. We're going to initialize all of the elements with a negative sales total. We do that in the first for loop. In the next for loop, for each salesperson in all salespersons, we're looking at every single salesperson. And if the salesperson's total sales is greater than the last, the top sales element salesperson is the one of the top 5 so far. So we would just be moving our salespeople around. And then lastly, we would be displaying our top 5 salespersons. So it's asking us which of the following is not equal to the number of times or items in the top sales array. The top sales is equal to length because that's the actual array. We know it is 5. The only thing that's different is the all salesperson length. Because if we come back up here, we can see that we're passing in all salespersons, and the array of all salespersons is not given to us. It's not known, so we can't assume that it's just 5 or the same as the top sales. Next, to adapt the algorithm to display the top 10 salespersons, what modifications are required? And the only modification is the array creation. If we look back up the code, we're looking at the top sales length for our arrays. So all we have to do is go up to the top right here in the 5th line and just change the number of elements. Currently, its top sales is equal to create an array with 5 elements. We would just change it to 10. And that is how we would do number 3. For number 4, if all salespersons only contain 3 elements, the display top 5 salesperson algorithm will display elements with no name and negative sales. This is true. And if we go back and we see the first for loop, we will see that if we have an empty array, we're still going to have an array that can have 5 elements. And so we would have an empty name and a sales total because our for loop doesn't run as long as we have a salesperson. It runs as long as our top sales length is. So that is number 4. And those are all the examples for this section. We covered running through this example. We covered these examples. And then we showed the difference between an array and a linked list. So that is how this section works.